Hello everyone, my name is Guillaume Cagnot. I'm a CFD engineer in Methodin, and today we're going to talk about assessment of natural ventilation in urban area with numerical tools. This presentation will last in total about 30 minutes. It will be about 25 minutes of the presentation itself and 5 minutes of question. During the presentation, you can ask me any question in the chat panel. I will answer you later at the end of the presentation. We will send you the presentation for those who give us their email. Okay, so let's start. So here are the contents. 4 main topics. First, we're going to talk about pressure fields on buildings and potential of natural air ventilation. Then I will give you some hints, some formula to assess the air exchange rate. Simple formula, but quite useful. I will give you also some hint how to optimize your openings thanks to the pressure coefficient. And I will explain you how to compute it using a CFD tool called UrbaWind. So what is the wind? The wind is it's actually air motion that induces force on the walls. For example, here we have a building, and the wind is coming from the right to the left. We get high pressure here, low pressure behind in the wake, and the wind is always going to go from high pressure to low pressure. So you got flow inside the rooms or apartments. So knowing that, how can you design your master plan? First, you should know that the pressure fields depend strongly on the geometry of your buildings. It will be completely different from square buildings than from, let's say, complex buildings. Another important thing to know is that the wind is completely different from your project than the one that you can usually get from the airport or outside of your project. So you have to be very careful. That's what I'm going to explain you now. So here is an example of windrows at the reference station, which is usually at the airport. So we got winds going to have prevailing wind coming from the east, and we got an annual average about 3.17 meter per second, 3.2 meter per second, let's say. So here the project, and we're going to have a look on windrows inside the pattern of the urban areas. So here, as you see, there is no buildings in between this point and the weather station. So the prevailing wind is still the same, it's coming from the east. There is no blockage effect. But if you have a look inside the city or the neighborhood, the prevailing wind is completely different. It's now coming from the south. Because here the wind is going to flow towards this direction. So it changed direction, but also it changed the mean speed. We don't have value here, but the more yellow color, more powerful is it. So here you see that when it's blue, it's weak wind. So why does that happen? Well, I will give you 3 main effects that's why it happen. The first one is called the corner effect. The corner effect is here, when the wind is going to blow from the left of the screen to the right with very tall buildings. You're going to have here the wind is going to hit the buildings, go downwards, and go around. So here you have a representation of the map, the wind map. Blue color means low speed, whereas the red one means strong speed, wind speed. So here you got acceleration. It means that here you will have lower pressure in this area. So corner effect, the first effect. Another one is called the wide effect. Wide effect happens when you got two buildings in a row, and you got what's going to happen is that the wind is going to hit the first one, but cannot go outside, so it's going to swirl until to go at the corner. Got big one and the smaller one here, and then here you get high pressure because it's going to hit, and lower pressure behind, and between you got intermediate pressure. So here another effect is called the Venturi effect. It happens when you got buildings in a row, then the wind is going to accelerate in between these two buildings. It has no choice than to escape from on the streets. This is what happened here. You got red color, so meaning acceleration. So here you got also acceleration means lower pressure or low pressure. So three effects. What you get in reality is a mixture of all of those effects: the Venturi effect, corner effect, and the wide effect. For example, in this project here, if we are taking into account this area, if the wind is going to blow toward this direction, you're going to have Venturi effect. Whereas here, we're going to have corner effect if it's blowing in the diagonal. So you can imagine that since you need to take into account several directions to have all the direction. So here, here you have another representation to show you the impact of the blockage effect. If the wind is going to blow from here to here, you will get high pressure, and then going to have lower pressure downstream. So how can you compute that? There is several ways. The first way is to run full-scale experiments, meaning that you're going to set up some met mast inside the city. This can be very expensive, takes quite some times. And then the second way to do it is running some wind tunnel experiments using scaled-down model. It's also an quite expensive way to do it. And the last one is, it happens, I was created let's say some decades ago, but is now getting more and more efficient and reliable. Those years is coming from numerical approach for CFD, for computational fluid dynamics. That's what I'm going to talk about later. So a little bit now for you to have some, say, some rules, some easy formula to get an idea of the potential of your natural ventilation. What you can use is this simple formula for two openings, 1 and 2. So using the coefficient, the pressure coefficient on openings 1 and 2, or the difference of those pressure coefficient, and also you need the surface of the openings and pressure coefficient, charge coefficient, meaning that the pressure loss inside the openings. And another one is the reference wind. You can actually simplify this formula by extracted the delta CP, which is a very important value, and the wind speed reference, and some equivalent surface. Here you have reference wind, which is upstream, and the delta CP. So it gives you flow rates, an estimation of the flow rates. How can you get the CP? Then you can get them from cards, from lineaments or Eurocode, or you can use some parametric models in standard case. Then just want to give you maybe another way, even simpler one, is to get from the delta CP, meaning that from the maximal maximum pressure minus minimum pressure, then you get the potential of natural ventilation. Here there is some example. They are extracted from Gardner and Morrow. It is applied only for tropical warm climates. 4 different range, which is delta CP below 0.17 up to delta CP above 0.53. And here it is colored here for each range. And here we have different represent different potential by color. So the highest one is the blue one. So how you see here, the blockage is phase quite weak. The buildings are very far away from the buildings here. So here you are a high positive pressure, and behind you have got low negative pressure. So it's about, if you are reading this scale, it's about almost let's say 2 delta CP equal 2, so it's a very good ACH. But if you are looking at this one, you've got sheltering effect here. So here the color of the delta CP is quite similar upstream and downstream. The potential is quite weak, whereas on the right side it is much efficient. It's green, so between this range. Here the same, potential is very good. It's quite useful, this kind of formula, but this is only for tropical warm climates. So now you know the flow rates. What you would like to do is to compute the flow rate for each room. So how can you do that? First, you need to compute the internal pressure. The internal pressure, you can use this formula, but first you need to solve the mass flow rates to equilibrate it. What is go in must goes outside. So once you equilibrate the mass flow, you equilibrate the pressure, and you can use this iterative process and try to adapt it using derivative of pressure. So here is an example from the windrows. You can compute the pressure coefficient and to get the internal pressure and get the flow rate through each rooms. Here the frequency table, here are the wind time series. So from that, what you can get is how can you assess the natural ventilation potential. So once you get your climate change data, you can compute your CP and give the position of the openings, and finally get the statistic of the air change rate. You can actually also export time series of mass flow rates. So how is it working for UrbaWind? It's in 3 steps. The first step, you need to set up the case. So you need at least the building's information, but you can add also topography, like here, and you can add porous element, like here in green. Once you set up the case, you need to run simulation. You need to mesh, which is completely automatic. You don't have to worry about that. Same for the boundary condition. This is automatic. And you will get the pressure coefficient. From that, you can, using the weather data and the characteristic of the openings, meaning that the surface of the opening, the opening angle, you can get the mass flow rates in each room or at each openings. You can also get the CP value for each opening, for each incidence of the, depends if you are referring to the wind direction or to the normal to the openings. But for UrbaWind, what you need as an input is building CAD information. All of them are STL formats. They are exported from most of the software, SketchUp, AutoCAD, Rhinoceros, Revit. Also the ground, it's STL formats, and the vegetation. All of them are STL formats. You need also weather data. They are else say frequency table or time series. All of them are input for UrbaWind. And once you have compute the CP, you can first export the wind rows inside your master plan, but you can also export the CP in the buildings, compute the time series of exchange rates, and so on. One important data you want to have, this is one of the most important, since I said the flow rate depends of the reference wind, the U wind. So how can you get that? First, there are 4 of them. First one is coming from the national providers. So it is usually a self-service. For example, here it's coming from France, from Japan, from UK. Another way to get it is from free weather data providers such as NOAA. So you will get thousands of weather data all over the world. Please check on their website, it's quite easy to use it. Another way to get it is from US Department of Energy. It's quite straightforward. Also, if you look on the internet, you will find all the information required. Another way to get it is coming from the software. Like this one from Meteornom. There are all other software that can provide you with this information. It's just an example. Another way to get it is from a simulation called meso scale simulation, and some example like 3-tier and meteor group. So how can they be input of UrbaWind? Well, you need most of the case some conversion, but it's quite straightforward. So for the time series, what you need for UrbaWind is just 2 columns, the direction and the mean speed. That's all you need. So in some ways, you may need to try to simplify your data, your wind data. It's quite straightforward using Excel. Just some exception for this one is the format from those software. This software of the website of US Department of Energy is EPW, which is directly read in UrbaWind. Another way it's from frequency table. It needs some conversion, but it's quite straightforward. So first you need to get correct wind data at your project, like here. But what you usually get is at the airport, far away from the city. So it's completely different. The behavior of the winds is different from here in the urban area, because here you have high mean speed but low turbulence density, whereas here in the urban areas you will get the opposite. So high turbulence intensity and low mean speed. Why that is because, well, you got roughness will be different, it will be higher, so the boundary layer will be different, it will slow down. And as we have seen before, the direction will change also. So you have to be careful of that. I would like to give you 3 examples we have made. One is coming from Réunion, so it's an island, French island. It was an existing buildings, and the owner would like to optimize the potential, natural potential. So you want to open new window like here, or maybe to optimize characteristics of the former one. So first we compute the CP, the pressure coefficient. We define those characteristics, and we can get the ACH statistic. If you want to take into account the Stokes effects, you can export those data, the CP, for example, in thermal tools, such as Design Builder, for example, or Energy Plus. Another one is from New Caledonia. It's a high school, and they wanted to use natural ventilation for the classrooms. So first you define here your project, compute the pressure coefficient, and you can compute the ACH for each rooms. The last example was in France. Here it was some office near Poitiers, and they want to take advantage of natural ventilation, but not only the wind, but also the Stokes effect. So first you need to define your projects and compute the pressure coefficient on it. You get natural ventilation from wind, which is in this graph here. You get mass flow rates here versus the frequency. So the blue one is coming from the red one is coming from the wind, and whereas the blue one is the wind plus the Stokes effect. So as you can see, for high volume flow mass rates, it can be very important, the effect of the Stokes. But you can add it with simple formula. You can find literature. A little bit about the performance of UrbaWind. Here you get 4 examples from the small radius to large radius. So here a small radius will be about 20 detached buildings. This takes about 5 minutes for one direction, and it takes about 400 mega octave of RAM. For larger scale 200 meter radius, which is suburban, it can be 25 minutes for 1.6 gigabytes. 360 meter radius could be up to 4 gigabytes and 160 minutes. And for a very large and complex, because 500 meters radius, which will be 1 kilometer square, with buildings about 100 meter high, very complex. It's about 16 gigabytes of RAM and about 20 hours. All those computations are done using this configuration. For the last scale, it seems to be quite huge computation time, but if you analyze other software of the market, it is much more efficient because we have optimized machine process and also the iterative process for the CFD equation. Everything will be optimized, so it's much more efficient than other software. Okay, now it's time for you to ask me any question. I will be pleased to answer you back. Um, Otherwise, you can send us email to info@methodin.com. Okay, if you don't have any more questions, I will end the session. So have a nice day and take care. Bye bye.